like the maximum allowable frequency for discrete time signal is fd equals to half cycles per sample. Similarly, the maximum allowable frequency for a continuous time signal which is about to be sampled will be fmax equals to fs by 2. This comes from the previous slide where it says that the range of f has to be between minus fs by 2 and fs by 2. Thus, the maximum frequency which can be present in a continuous time sinusoid can be fmax is equal to fs over 2. Or this also means that fs minimum can be twice of fmax, which means that sampling frequency cannot be less than twice the maximum frequency present in the continuous time signal. So this indicates that if we are about to select an appropriate sampling frequency, then we will have to look at the maximum frequency present in the continuous time signal and then multiply it by 2 in order to get the minimum appropriate sampling frequency for that signal. Now the question can be that whether we select fs or we select fmax. So it depends on the application. So for example, we are dealing with a condition that sampling frequency is fixed and we are told that yes, sampling frequency is 100 samples per second and you cannot change it. So if you know sampling frequency is 100, then 100 divided by 2 is going to be 50 Hertz. So then you will say, okay, because my fs is fixed, what I can do is that I can sample any signal up to a frequency of 50 Hertz and not mess it up. So this is one condition. Or another condition can be that we do not have fs as fixed, rather we know that we are working on a audio signal or a speech signal which has a maximum frequency of, let's say, 5000 Hertz, and there is no frequency beyond that. So for a signal having a maximum frequency of 5000 Hertz, we will multiply it by 2, so that will give us a minimum sampling rate or sampling frequency of 10,000 samples per second. So whether we select fsmin or fmax, this depends on the condition or the application we are about to handle. Right, so just connecting with the previous slide, the minimum sampling rate or the sampling frequency called fs, at which a signal can be sampled without introducing any error, is called Nyquist frequency. And Nyquist frequency, as we have seen in the previous slide, is twice the maximum frequency present in the continuous time signal. So if we know the maximum frequency present in the signal, then we multiply it by 2. This is called the Nyquist frequency, which happens to be the minimum sampling frequency of the signal. Okay, so far we have discussed in theory what are the relationship between capital F, small fd and fs, and I have mentioned some points as well. Now this example will help us strengthen those learnings. So the example is from the book. I think this is 4.1. Here it says that there are two analog continuous time signals. One is x1t as cos 2 pi 10t, where 10 is of course 10 Hertz, and the second signal is x2t, which is cos 2 pi 50t, where 50 is the 50 is the frequency, analog frequency in Hertz for that signal. And what we are going to do is that we will be sampling both of these signals with the sampling frequency of 40 samples per second. And the example asks us to write down their corresponding discrete time signals expressions in the form of x1n n x to n. So let us do it in one by one fashion, and then we will move on to the observations. So taking the first part, we see that the signal was x1t as cos 2 pi 10t, and this is to be sampled at fs is equal to 40 samples per second. Now we know that xn, the generic formula is cos 2 pi fdn, or we can write as cos 2 pi f over fs into n, because we know that fd is equal to f over fs. Now we know both capital F and Fs. For this example, capital F is 10 Hz and Fs is 40 Hz. So this makes x1n as cos 2 pi 10 upon 40n, and simplifying we get cos 2 pi 1 over 4n. So our Fd becomes 1 upon 4 cycles per sample. Now one thing to note here, that Fd 1 over 4 is less than 1.2, which is the allowable range for the frequency we saw earlier. Now let us look at the other signal. The other signal was x2t is equal to cos 2 pi 50t, and it also had to be sampled at the same rate, fs equals to 40 samples per second, and everything else remains the same. Now f2 is not 10 Hz, it is 50 Hz. Therefore x2n will be cos 2 pi 50 upon 40, thus making it cos 2 pi 5 upon 4n. So fd becomes 5 over 4n. So fd is equal to 5 over 4 cycles per sample, which is, we observe that greater than half. So we note here that we have gone into an area where frequency is beyond the allowable range. So in the further slides we are about to see that what happens in case such a scenario occurs. Okay, so we continue with the second part, where our discrete time sinusoid expression came out to be cos 2 pi 5 over 4n. We recall from the second postulate of discrete time sinusoid that the discrete time sinusoids having their frequencies apart by an integer multiple of 2 pi are identical. So what we do is we split 5 by 4 into a combination of a fraction and an integer, and we make sure that the fraction is a number which lies between minus half and half, and then whatever integer suits, it can be 1, it can be 2, it can be a negative integer, but a combination of a fraction which is between minus half and half and an integer, so that when you add them up, it gives you back the original frequency. So 5 by 4 can be split easily into 1 by 4 plus 1, and using the formula of cos alpha plus beta, so we get cos 2 pi 1 over 4n, cos 2 pi 1n minus sine 2 pi minus into n into sine 2 pi 1n. Please ignore this. Okay, sine 2 pi 1 over 4n into sine 2 pi 1n. This is simple cos alpha plus beta expression, which is now expanded into this format. Cos 2 pi 1n going to be 1. Sine 2 pi 1n goes to be 0, making this entire expression as 0. And we come down to, it is simplified into x2n is equal to cos 2 pi 1 over 4n, which we see that is the same expression as that of x1n. Now this is an important finding. What we see here is that both x1t and x2t are generating same values of discrete time signals when sampled at fs equals to 40 samples per second. Right, so now let's look at some of the things we can extract and observe from these findings. We have seen that both of the signals x1t and x2t are generating same values when sampled at fs equals to 40 samples per second. So the problem is that if we don't know x1t and x2t, but we are just provided the sampled versions x1n and x2n, so you are handed over these two signals directly and are asked that, okay, can you tell me what were the original analog signals from where these signals come from? So we will not be able to identify correctly the source of their analog signals because both of these signals are now generating the same samples and it will be difficult to identify the sources. This observation is called aliasing, and we say that the frequency 50 Hz is an alias of 10 Hz when it is sampled at 40 samples per second. One thing to note here is that the difference between the 50 Hz and a 10 Hz signal is also 40 Hz, which is also the fs of fs in this case, which is 40. Okay, so I repeat that when such a scenario happens, we say that a 50 Hz signal is an alias of 10 Hz when it is sampled at 40 samples per second. So if you want to look at the reason why such a scenario is happening, then basically what's happening is that we are not following the Nyquist criteria completely. We know that Nyquist criteria says that minimum sampling frequency must be twice of the maximum frequency present in the continuous time signal, and we have sampled two signals. One was with a frequency 10 Hz and the other was with a frequency 50 Hz, and our sampling frequency was 40 Hz. So for a signal with 10 Hz frequency, the sampling frequency fs is already 4 times that of f1, that is 10 Hz times 4 is 40 Hz. So we are fine here, we are meeting the Nyquist criteria. But whereas when we look at the frequency of the second signal, which is 50 Hz, the sampling frequency fs 40 is less than twice of 50. This is the problem. In order to correctly sample a 50 Hz signal, the minimum sampling frequency must have been 50 multiplied by 2, that is 100 samples per second. That was the minimum fs for sampling a 50 Hz signal. But we have sampled it with a far lesser sampling frequency, which is 40 Hz, thus creating the problem. Right, so one thing, there are a few more observations. The first thing on the slide is to note that 50 Hz is not the only alias of 10 Hz when sampled at 40 samples per second. We have already seen that the difference between 50 Hz and 10 Hz is that of fs. So similarly, taking the note, 50 Hz is an alias of 10 Hz. Similarly, 90 Hz will also be an alias of 10 Hz because 90 and 10, they differ by 80, which is a 2 times 40 difference. Similarly, 130 Hz will also be an alias of 10 Hz when sampled by 40 samples per second. The reason is that the difference between 130 and 10 is 120, which is 3 times 40. Similarly, we can go in the negative direction. A minus 30 Hz signal will also be a alias of 10 Hz signal because the difference between 10 and minus 30 is 40 by 1. And similarly, you can go in further in negative direction. Minus 70 Hz will also be an alias of 10 Hz because 2 times 40 is 80, and 80 is the difference between 10 and minus 70. And what you can do, I will advise that all of you try and calculate some initial values of cos 2 pi 9 over 4n, 13 over 4n, minus 3 over 4n. Take values of n as 0, 1, 2, 3, 4, 5. That's it. 5 to 6 values of n, and try to calculate the values of all these three signals. You will find out that all the values are coming out to be identical, which shows that yes, 90 Hertz and 130 Hertz and minus 30 Hertz, all of these signals are alias of 10 Hertz signal when sampled at 40 Hertz. Last observation here so far is that except the FD, which was 1 over 4, all other frequencies which came out to be as 50 over 40 as 5 by 4, 90 over 40 as 9 by 4, 130 over 40 as 13 by 4, minus 30 over 4 as minus 3 by 4, or minus 70 by 4 by 40 as minus 7 by 4, they fall outside the permissible range of FD, which was minus half to half. That's why all of these frequencies will generate identical values as 1 by 4.